So, so we need to move on here with what we have going on. So, excuse me. So first of all, just of course with the stuff we're doing with OneNote here, you'll notice again, folks. Of course, we left off at this point last time. And of course, obviously, I tried to put in here a day break that we had here, but again, notice I left myself way too much space for these. Yeah. Okay. So you're going to see that occasionally as we go through and do some of this work. There's going to be massive amounts of space in there. If I have time when I export the finished version, I will fix up and lose the space. But chances are I'm going to get busy and it ain't going to happen. Okay. So there's going to be a lot of blank space in this application. Okay. So I guess we should scroll back up here for a second. So to this point, folks, again, all of these integration by parts problems that we worked last time, again, like I said, I tried to imply when I started working this problem, folks, there seems to be an obvious pattern here because everything we've had to this point has kind of been a polynomial times a function, exponential, trig function, something along those lines. And the stuff in front just always went with the u, and that kind of odd function where the exponential or trig functions always kind of went with dv. Yep. Okay. But as I said, you're going to be careful with patterns because I can break them. Okay, and we'll definitely break them on occasion. Okay. And so let's kind of take a look that definitely don't fit that pattern. So here we go. So so at this point here, my pen's working. Yeah, good. So at this point, this one looks significantly different than the one we worked last time, okay? In the sense that there's nothing in front of the function, and B, just the same thing. There's just a single function here, okay? So this doesn't look like necessarily an integration by parts problem up to a point. Or other points, you can say, well, you know what? We'll try the same pattern that we did last time. We'll say, okay, I got a U, I need a dV. So, okay. And just if we kind of try to, quote, follow that pattern, well, since there's really kind of nothing in front of the function, we could say, all right, well, there's just a 1 there. So let the u be a 1, because that's the quote unquote stuff in front of my function. And then the other function over here, or the other stuff, the function left over, we'll put that with the dv, just like we did last time. Okay, now, I'm not going to address the u part over here. This can cause us some issues on occasion. The point I want to make out with this real quickly, though, is remember how we compute the v. How do we compute the v? We compute v by integrating dv. Yeah. Okay, so that means to get v, I have to do, sorry, bad writing, worse than normal today. Not working. There we go. Okay, we have to compute that integral. Yeah. Can anyone see the problem? In order to evaluate our integral here, yeah, if I take this choice of u and dv, that means I have to do what? I have to, evaluate the actual integral we're asked to evaluate, yeah? Or in other words, folks, we have to know the answer to get the answer. Yep. Okay. So, good choice for u and dv? Well, probably not, yeah? If I have to know the answer to get the answer, that means for us at least, that choice can't possibly work for us, okay? So again, if you try to follow this pattern stuff, that again, it looks like exists there, okay? It gets you in trouble, okay? In this case, at least in this particular case. So we need to do something else here. So let's try something else. So u equals, v equals. Okay, now, also keep in mind what I said last time, okay? Oh, did I forget to record? Yes, I did. Thank you. Thank you. Sorry, I moved that out of the way too quickly. Apologize for that. There it goes. Now we're recording. This is what happens when it's kind of off the screen here. I missed the reminder to do that. Okay, so sorry about that. Okay, now, also, if you remember what I was kind of doing last time, folks, is I tended to say, you know, look for ways to get rid of the problem. And of course, the previous problems, it was always that stuff that was sitting in front of the trig function exponential. I could get rid of that somehow, life would work for me, okay? Now, at this point here, it kind of works the same way, although you want to be a little bit careful, because the problem here, of course, is the fact that I've got this exponential to start with. I don't know how to integrate that. That's, of course, why we're doing the problem. Yeah, I'm trying to figure out how to integrate natural log. So at some level, we're going to take the same idea in the sense of, I don't want to say in this case get rid of it, because in the last case I got rid of the x or the w squared or whatever it was sitting in front of there by differentiating. I completely got rid of it. Yep, so it completely disappeared eventually, at least. In this case, I want to kind of look at it the same way, although again, I want to be careful with saying get rid of things because it's not going to work in my next examples we'll talk about there. The same idea. So since I don't know how to integrate this thing, the natural log here, maybe we could just kind of, again, I don't want to say get rid of it, but maybe convert it into something else, yeah? Now, again, obviously we can't put this also kind of, ties to what we were doing up here. I obviously, again, can't put the natural log with dv, so the only real option then is to put it over here with the u and hope things work out, yeah? Okay, now, deal with the dv here in a second. But again, notice what I said, kind of trying to kind of get rid of it or change it into something else that works real nicely for us because what's the derivative of natural log? Anybody remember? 1 over x, yeah. So I'm not getting rid of the term, but what I can do is change it into something else that'll hopefully be useful to it, right? So again, not getting rid of it, but changing it into something else. Okay, so 1 over x dx here. Now, the last part is this dv here, folks. The dv is always everything else that's left over, but in this case, the stuff that's left over is basically our dx over here. Yep. So that is literally what dv is going to be, just straight up dx. Okay. Rare that that's going to happen, folks, but when it does, we'll do it. Okay, it happens in this case. Now, in this case, just to make it clear again, v then is just integral of dx, yeah, and integral of dx, of course, is just x, yeah. Okay, so simple enough here in this case. So there's our v. Okay. All right. Now I claim this is going to work, but everybody kind of followed my choices here on the work I did with that stuff. Yep. Okay. So let's actually try to work this problem then real quickly. So natural log of x dx. All right. So again, remember our formula. It's let's go clear back up to it. Take me as long to scroll up. But remember what it is. It's u times v. So x times natural log of x. Yeah. And then minus integral of v du. So in this case, I'm going to actually put everything in here, just a point I want to make with this. So v du, so x from our v, yeah, 1 over x from our du, and then our dx, yeah. All right, so if I just straight up use our formula, that's what we have, right? Everyone agree? Okay, now, again, folks, this is not something that you need to do on a regular basis, but it happens often enough that I need to make the point. I got to integrate that, yep. What should I do first before I integrate that? Distribute or simplify, yeah. The problem here, folks, is that I will get folks with this integral here literally trying to integrate this as is. And that's just silly. As is, it's pretty much impossible to integrate. Okay, so make sure, folks, that you look. Is there any kind of simplification or canceling that can be done before you start doing the integral? Right? That's just it just doesn't happen often. But in a case like this, yeah. Down first. There we go. The simplification is dead simple, yeah, because they just cancel, right? So just a dx, oops, sorry, equal sign there. Sorry about that. But just cancel in this case, yeah. Okay. So again, look for that stuff because otherwise, trying to do this integral again as is just pretty much impossible. But once you realize, okay, if I just cancel the x's, I get something that's dead simple to deal with. Okay? So at that point, then we can kind of go ahead and finish out what we got here. So x natural log of x, and then equal sign there. Sorry about that. Is minus x. We're done with our integration here, so we'll just tack on our plus c at that stage. Yep. Okay, so simple problem. Sorry, I had to take a drink there. Simple problem once you see what to do. Yep. Okay, without seeing the right substitute or the right choice for u and dv up here, this is actually a really hard problem. Okay, so but once you see again the proper choice, it's not terribly bad. Okay, so everybody follow with this one. Quote unquote simple. Yeah. Yeah, like I say, it says simple when you watch me do it, not always as simple when you have to do it on your own. Yep. Okay. All right. So there's that. And again, I left myself way too much space for this for some reason. So again, lots of extra space here. Okay. So the last problem here, folks, that I want to take a look at here with this is again, this is very definitely a pattern break, okay, in the sense that clearly we're not having, again, any kind of polynomial in front and then an extra function out there, anything like that. And not only that, well, actually, I'll make my next point here in a minute. but this clearly breaks the pattern from anything we've done to this point. Yep. So again, like I said, pattern breakers, and again, folks, there's a couple on the homework. I'll comment on that here in a second, that break it even worse in some ways. Okay. So again, you got to be kind of careful about seeing patterns on these things. Okay. Now, next thing here is we need a U again, and we need a DV. Okay. Now, again, comment I was going to make a minute ago, better to make it right here at this stage, I think. To this point, again, I've always said, can I get rid of something? Because again, the problem here is if I didn't have the exponential, if I didn't have the trig function, this would be a dead simple problem. It'd be really, really simple, okay? But I've got them there. And so up to this point, again, I've always said, okay, can I get rid of a term in here? Or in the case of that logarithm one, can I change it into something significantly different that'll maybe make something good for me? Yep, okay? Problem is we know, we talked about this, I think, with my first problem, this exponential here, it ain't going away. Yep. If I differentiate it, if I integrate it, it stays an exponential. I cannot make it go away. Right? The cosine, clearly I can change it, but the only thing I can do is change it into a sine. It's still going to stay a trig function, unlike with the logarithm, where the logarithm kind of dropped out and changed into something else. Right? So in this case, I can't get rid of the exponential no matter how hard I want to. And likewise, I can't really get rid of the trig function. It's always going to be a trig function there. So this again comes down to, again, even what I said, look for kind of ways to get rid of things or change them. Even that gets you into trouble if you look for that kind of stuff. Right? So here's a case where that's definitely going to happen for us. Now, again, we got to pick a unit DV here. Again, I don't want to put the whole thing over here with DV because that gives me exactly the same problem I had with the logarithm. Got to know the answer, get the answer. Yep. Okay, so I don't want to do that. Likewise, I don't want to put the whole thing over here with the U because again, we could differentiate that, but that's a product rule, and the product rule is going to stay with an exponential times a sine, exponential times a cosine. So now I've got two terms in there that are basically the same problem. Yeah. Right. So again, I don't want to put the whole thing with DV. Don't want to put the whole thing with U because either I can't do it or it's really, really unpleasant, and I probably still can't do it. Yeah. Right. So at this point. This is, I don't say this is a trick problem, folks. This is another one of those that once you see what to do, it's not, I shouldn't say it's not bad. Once you see what to do, you know what to do. It's still kind of an unpleasant problem at some level, okay? But you got to see what to do to know what to do. Okay, it's not something you're necessarily just pick up, hey, here's what you do. Now, this is also a rare problem, folks, in the sense this is the only problem I think where this happens, the only one that I'm aware of where this happens. An exponential times a sine or a cosine. I could do the same problem here with the sine here if I wanted to. We actually see that here in a second. But it turns out I could put the exponential with either the u or the dv and then put the cosine on whichever one that I want. In other words, folks, it really is not going to matter what choice I make here. Okay, if I want to put the exponential with the u, I could do that. I want to put it with the e to the v, which I do. That's where I'm going to put it. Okay? Now, again, you want to put it with u, be my guest. That just means the cosine for me comes over here on the u. If you put the exponential on the u, that means the cosine comes over on the dv. Okay? Again, in this case, it does not matter. Again, folks, this is the only time, or the only case I can think of that happens. Okay? Every other case, you pretty much have u has to be u, v has to be dv, has to be dv. Okay, so it's the only option. Oh, the other comment I should make here, folks, again, is I hope no one has an issue with the fact we're using thetas here. Yeah, it's just a letter. Right? We're not used to using Greek letters for these things, but it is just a letter. And of course, I'm using it here, folks, because in a couple of sections, pretty much every problem is thetas. Right? So better get used to using thetas. All right. So now, before I go on here, folks, why did I do the choice I made? Because I said it can go either direction. Because I would rather integrate exponential than integrate cosine. Yep. Okay. I always get the plus minus signs right when I differentiate cosine, but I always screw them up on occasion when I integrate cosine. Okay. So I'd rather differentiate cosine just so I don't mess up the plus minus part of things. Okay. That is literally the only reason I threw the cosine on the u and the exponential on the v. Okay. If you're good at keeping track of this other plus minus signs and integrating trig functions, be my guest. Put it in the DV. Okay. Not an issue. All right. So, all right. So let's go ahead and finish this out then. Or I should say finish out, do this step. So again, derivative of cosine's dead simple. There it is. And again, integration of e to theta, again, dead simple. So this. All right. Now, let's go through our integration by parts formula here. So what do we got here? Again, so we got u times v. All right. So go minus integral of v du. Now again, watch your minus signs. Yeah. So v du, and the du, of course, has got a minus sign there, folks. I'm going to go ahead and factor that out. Actually, be careful because last time. I'll go ahead and factor that out and change that into a plus then. Yep. Okay. So you just watch the minus signs get really, really easy to again see a minus sign, two minus signs, only write one of them down. Yep. All right, and then the rest of our problem. So e to the theta, sine of theta, d theta. Okay. Well, the idea here again, yeah, is to take an integral that I can't do, write it in terms of one that hopefully I can do, and yeah, I don't really see a difference between a cosine and a sine. I mean, if I can't do a cosine here, I surely can't do a sine here. Yeah. Okay. So, so I got a problem here, folks. This is still an integral I really just simply cannot do. Right. For the same reason, I can't do the first one. Okay. So I'm still stuck with one I simply can't do. At this point, the only thing I can think of to try is say, you know what? We saw this, you know, in that was it a couple of examples. Last example yesterday, I guess, was sometimes you got to do integration by parts more than once. Who knows? Let's see what happens. Yeah. Okay. Let's try it again. Just to see. Okay. So so let's do a U here and a DV. And again, I'll use different colors here. Again, folks, just kind of watching again the fact that we've got U's and V's here in two places here. Obviously, the U's and V's initially are now gone. We're doing a new set here, so different colors to kind of make that point. Yeah. I'm going to go ahead and put the exponential again with the DV for the same reason as last time, and then I'll go ahead and again throw the sign on the U there. It's simple enough to do our work here. So the U, and I'm already not liking this. Cosine of theta there on the du, and v, of course, is simple, so e to our theta there. Yeah? Okay. Well, I'm not sure I like this, but let's go ahead and do this. So bring this down here. Okay, so again, I got my first term here again. Let's keep that there. So e to theta, cosine of theta, got our plus there. Again, remember, folks, if you got a coefficient in front of this, make sure and watch your brackets. Yep. In this case, you don't have to worry about it, but in other cases, you'll have to. Okay. All right, now, again, at this point, let's do our new integration by parts. So, again, new integration by parts with this integral here. So, u times v, or v times u, how you want to think about it. So, e to the theta sine of theta minus integral of v du. So, e to the theta cosine of theta theta. Yeah. That didn't do me a whole lot of good, did it? Now I just got right back to where I started. Yeah. Okay. So we could try integration by parts again, but would that do me any good? No, because if I integrate this by parts again, all it's going to do is bring it right back up to the exponential times sine. Do it again, back to exponential times cosine. Basically, I'm just sitting here and just kind of pop it back and forth, back and forth, back and forth. Yep. Okay. Now, obviously, we've got an issue here, right? So let's ignore this problem. Who cares? Let's do something else. Let me insult everybody's intelligence, and I am trying to insult it. So please be insulted. Solve for x. What do you do? Solve being insulted. What do we do? Yeah, you add the x to the other side. Yeah, okay. So 2x equals 3. We'll divide by 2. Yeah, absolutely. Yeah. So I'm insulting everybody. Please, all right? Y'all can do that. Okay. All right. So why did I do that? Yeah. And so the x can be alone. And think of this as well. This x here, folks, it's just a variable. Yeah, what's a variable? Variable is just used to represent something I don't know what it is. Yeah. Okay. So how about, because I'm trying to do here, right, is I'm trying to integrate or figure out what this integral up here is. I don't know what its value is. Yeah. Okay. So why don't I come back here and say, you know what? Here's the integral I'm trying to do. Yeah. And of course, I've got exactly the same integral sitting right over here. So why don't I just call that x in my head temporarily? I'm not going to write down an x, but think of, hey, there's kind of my x in my equation I had sitting down here. Now, obviously, I don't have a 3 here. I've got something much more complicated there. Yeah, right? But if you think about it, I've got something I don't know its value for, integral, or x, I want to think about it, equals stuff. Yeah, it's messier than a 3, but stuff. minus the same thing, right? So all I have to do then is think about, okay, well, again, let's scroll up here a little bit. What did I do down here? Well, I added the x to both sides. Okay, fine. Let's add our integral to both sides, okay? I've got the integral sitting up here. Add another one on. How many do I have? I got two of them, yep. So if I add that integral to both sides, I'm going to have 2 times the integral of e to the theta cosine of theta d theta, right? Equals, well, the stuff that's left over, and that's just e to the theta cosine of theta plus e to the theta sine of theta. Yeah. Okay. This is a tricky little problem, folks, and this is a trick that you don't have to do terribly often, but it will show up down the road one more time before the semester is over. Right? So everybody kind of follow what I did there. So again, integration by parts a couple of times. And yeah, it doesn't make sense why I'm doing it because it seems to be circular. I get that. But once we do integration by parts a couple of times again, I didn't have room to write this, of course, but again, we've got this integral, yeah, sitting down there. Okay, so my integral here equals that stuff there minus exactly the same integral. So since I want to figure out what the value of that integral is, all I had to do then was simply add that to both sides. Okay? Now, again, if I want to know what's the value of this integral, that's what we're having to figure out, yeah? Oops. Sorry. Okay. So if I want to figure out the value of this integral, what do I do? Thoughts? Oh, and what did I do up here, folks, with this insulting equation? I divided by 2, yeah? Okay. So what do you think I'm going to do down here? I'm going to divide by 2. I got the number that's sitting in front of the x, written as an integral, of course, but the stuff I want to keep this over here on this side, just I'm going to keep the x over here, so I divide it out by the 2. Well, guess what? I'll divide out by 2. Or for me, I usually go ahead and divide or multiply by 1/2, just a little bit easier to write. Yeah, but divide out, multiply, however you want to do it. E to the theta, cosine of theta, plus e to the theta, sine of theta. We're done. So plus 6. Okay, this is a very, oops, sorry about that, very tricky problem, folks. Okay, but there it is. Okay, so any questions on this? I kind of follow what I did with this. Again, this is not something you're going to have to do a lot, folks. This is not an integral you run into terribly often, but I want to make sure you can do it in case you do run into it. Okay, so any questions? We're going to follow. Online, you guys doing okay, hopefully? Again, I know this is a little bit confusing. This is probably of all the stuff in here, folks. This is definitely one of the harder ones in here. I have to think about this in a little bit, probably. Okay, so any questions on this before we move on to new stuff here? No. Yeah, all we did is just, I mean, again, just basically integration by parts. Yeah. Okay. I just simply just said, you know, I need to do this here. I had to pick a U, pick a DV, and I know this is hard to justify, but you just this is one of those cases you're going to have to kind of trust me. I hate to say that, but basically, I can put the exponential in this case for exponentials times a sine or a cosine. It only works in this case. Okay, I can put the exponential either with the DV or the U. Doesn't matter. Okay, and then the cosine just goes in whichever place I didn't use it for the exponential. And again, that's just one of these things. This is just the way this problem works. Okay? I know that's a bad way to say that, but it is just the way it works. Okay? Again, you want the exponential here, cosine here, you could surely do that. You get exactly the same answer by the time it's done. Right? So this is the choice I went with. So I went with that choice. Then simply went through my integration by parts through the formula here again. Reminding my minus sign there merged up with that one. And then again, just saw exactly this, basically the same integral here. So I said, okay, well, I'll try integration by parts again, see if that works for me. So exponential on the dv again, sine is case on the u. Went through my formula again. Yep. Okay, so again, I got my original part left over there from the first integration by parts. And then just do the second integration by parts there, do the formula. Okay. And then at that point, again, it was just simply a case, and this is something, folks, I would never expect anyone to know to do this until you've seen it done. Okay. And now that you've seen it done, you know it can be done. Would you think about doing it? Well, probably not, and that's fine. Because again, so I'm going to come up a couple of places. Right. So it's not something you're going to have to worry about unless you see a problem like this. You don't need to worry about it for the most part. Okay. And by this, I mean exponential times a trig function. And you say, okay, well, I'll simply take this integral here and I'll add it to both sides, just like we did here with my equation. So take the integral, add it to both sides. Yeah, I got 2 of my x's or 2 of my integrals. Okay, equals the stuff that was left over, and then simply say, well, I have this coefficient here, whatever it is, 2 in this case, so I'll simply divide out by the 2. Okay. Okay. So again, like I said, it's tricky. I'm not going to say it's not tricky, folks. It's definitely one of the trickier problems that you're going to be asked to kind of deal with. Once you see how to do it, they're not bad, but again, it's that seeing part that's rough sometimes. Okay, so making sense, everybody. Yep, hopefully. Okay, so that is integration by parts, folks. So quick little comment on the homework here, folks. At this point, in theory, you are capable of doing everything. Okay. Now, having said that, folks, numbers 5 and number 6, I'm not going to say anything about those in class. In theory, you are capable of doing those. Those are pattern breakers, right? Those are very tricky problems, right? In some senses. Once you see how to do them, in particular, number 5 is actually probably one of the simple ones in there. Once you see how to do it, okay? And once you realize that it doesn't quite follow the patterns, because they're going to look like they follow the patterns to a certain extent, okay? So I want you to be careful with that kind of thing. We're going to have a help session next week, okay? Whenever this, I said this is going to be due tentatively on Wednesday. At this point, I think it might still actually be Wednesday. Okay, so if it's going to be due on Wednesday, on Tuesday we'll have a help session, and I will I'm sure get a question about 1 or 2 of those, and we can work on something similar to those, okay, to see how they work. Okay? So but at this point, please give them a shot, okay, and we'll see if we can, like I said, on a help day next week, we'll work on similar-ish being very, similar-ish to those things, okay? So, all right, but please give them a shot ahead of time, okay? All right, so unfortunately now we need to kind of move on to the next section here, okay? So integrals involving trig functions here. All right, so I guess the thing I want to kind of say about this section, folks, and this is in a I always want to be careful about how I say this. This is Calc 1, literally Calc 1. Okay, all we're doing in this section are U substitutions. That's it. The problem is, folks, and this is the problem, okay, is most of these ain't going to be obvious obvious substitutions, okay? And we'll get to what's going on in this section here in a minute, but I do want to start with one that is literally just a Calc 1 problem. Okay, something you may or may not have seen it back in Calc 1. I hope you did. But if you did, let's work through one here. So this problem sitting right here at the top. Yep, okay. So simple integral of cosine times sine to the fifth. That's it. Now, if you've seen one of these before, first of all, remember, of course, that when we write sine, so when we write, sine to the fifth of x, yeah, what we really mean, right, is sine to the fifth, yeah, okay? In other words, the exponent here comes out there, yeah? We just simply don't write these brackets in here because, well, we don't. Okay? So remember then that this sine to the fifth here then, yeah, is the same thing as this. Okay? Now, having said that, that should make the quote unquote make the substitution easier. What do I mean by that? Well, usually our substitutions were almost always what? They were stuff inside things, yeah? Right? So it makes sense then that maybe we can use sine as my substitution, right? Okay? So if I use sine as my substitution, then what's du? Well, du is cosine of x dx, yep. And what do I see up here? Well, I see a cosine of x times the dx sitting right there. Yep, okay. So what's that mean for me then? Well, that means for us then is what? That these 2 bits right here are just our du from our substitution then, right? Okay. And then what do we got left over? What we got left over is this sine to the fifth here, yeah? And that's just going to be what? Well, that's this. Oh, but sine was just u, so that's just going to be u to the fifth, yeah? Okay, so if you kind of do the problem properly then, so integral cosine sine to the fifth dx, yep. Well, upon doing my substitution, again, the sine to the fifth, that's just u to the fifth. All right, there it is. And again, the cosine times dx, well, again, that's just the du. So u. At that point, that's a dead simple integral. Yep. So 1 to the 6, u to the 6. But I see no reason to write the u down. We know what u was. That was sine. So sine to the 6. Whoops, sine not dx. Right? I'll see. Sorry about that. quote unquote simple again. Yeah, that's a Calc 1 substitution. That's all it is. Okay. Now, everybody kind of follow with that. And again, remember I said the other day, folks, your substitutions are going to be kind of important you understand them. Yeah. You're starting to see now why they're important you understand. Okay, because every single one of these problems in this section, folks, is going to come down to this kind of substitution. Right. So you're going to have to be able to do these substitutions. All right. Now, let me show you the problem that I actually want to work. Okay. That's the problem I want to work. Right? What's missing? Yeah, that cosine. The first one I did had a cosine. Yeah. Okay. This one doesn't have the cosine. Right? Now, this is still a Calc 1 substitution. It just shouldn't keep scrolling down here. It just ain't that one. Right? Because if I try to do a u equals a sine, right? If I try to do u equals sine, why will u equals sine not work? It won't work because you're missing the cosine, right? Remember, all the x's have to get converted over into u's in some way, and that includes that dx back here. And yeah, you could get rid of the dx using this, but you'd pick up a cosine in the process, right? Okay. So this substitution that we had used up here this first time simply won't work down here because it's missing the cosine it needs for that differential to work for us, right? So u equals sine here, make this clear, won't work. Okay. Now, again, this doesn't mean this isn't a Calc 1 substitution, folks. It absolutely is. Okay, it's just not an obvious substitution, and that is kind of the point of this section, folks. There's 2 points, I guess. One is being able to deal with these things involving trig functions. Okay, that's one of the things we have to deal with. The other issue that we have to deal with, though, and this is going to be kind of important again, folks, is to understand that in Calc 1, the integrals are pretty much doable right off the bat. Okay, pick your substitution, and that was it. Right? So that's all you had to worry about. Most of the work that we're going to be doing from this point on here, folks, as far as integrals go, you can't do right off the bat. What you're going to have to do is do some work ahead of time to get them into a form you can actually do the integral form. Right? That is the point of the next 3 sections of the different types of things you sometimes have to do to these problems to put them into a form you can actually do. Right? So the first thing I want to do here, folks, is I'm just going to start working the problem. What I don't want you guys to worry about is why I'm doing anything I'm doing, right? I want you just to follow the steps. You should be able to understand every step that I'm doing, right? Except the whys. It's easier to explain the whys when the work is on the board or on the screen, right? So let's do some steps, make sure you understand the steps, then we'll come back and discuss the whys, right? So again, do not worry about why I'm doing some of the stuff I'm doing at this stage. Just accept the fact that it's what I'm doing because I want to do it, okay? And again, come back and discuss the why once I get the work done. Okay, now, first thing I'm going to do, because I can and because I feel like it, is well, first of all, I guess let's get off the side over here, yeah? Oops, man, sorry. Trouble with that these days. Okay, so off the side over here, let's just kind of again say, oh, I don't know, x to the 5th, okay? Would you all agree, basic algebra, I can write x to the 5th is x times x to the 4th, yeah? Simple algebra, exponent work, we all could do that, right? Well, I'm gonna do the same thing here. I'm gonna strip one of the signs out, and leave the other 4 left alone, yeah? So, sine the 5th, sine times sine the 4th. It's just, again, the same idea as the stuff we got over on the side. Yeah, that's all this. So nothing new there. This is just algebra. It's just algebra, again, using stuff that, on trig functions rather than x's. Simple stuff, though. Yep. Okay, now, again, off the side again. I don't want to use a 4 off the side here, so I'm going to use a 6 instead. So you'll see why I'm using this here in a second. So I've got x to the 6. 4 up here, yes, I know. We'll see why I wanted to use a 6 down here in a minute. Would you all agree if I wanted to, I could always take that x to the 6 and write it as x squared cubed? Again, simple algebra work. That's all it is, yeah? Exponent work, okay? Or if it's x to the 10th, I could write that as x squared to the 5th, yep? Or x to the 20th, I could write that as x squared to the 10th, yep? Notice when I say that, what am I doing every single time? It's squared to something, yep? Okay? The squared has to be here if the something is whatever I need to make that exponent work, which is also why I didn't want to use a 4 down here because 4 could be written as what? Squared Squared, yeah, 2 squared floating around. I also don't want to work the problem with 6 in here. Well, you'll see why here in a little bit. Okay, so 4 is kind of about the highest exponent I really want to do on these things. Okay, but you need to understand it needs to be squared to whatever it needs to be. That squared has to be there. Okay, so the next thing I'm going to do then is the same idea down here. This is sine to the 4th. So if I wanted to, a little bit of room to come down this way, I can write this then as integral sine of x. That's going to stay there. And then I'm going to take my sine to the 4th here and write that as sine squared. Yep. Okay. Yeah. Now again, had that been sine to the 6th, I'd have sine squared cubed. Been sine to the 10th, I'd have sine squared to the 5th. Okay. But again, I need that to be a sine squared there. Okay, for this all to work. Again, the inside one has to be squared. The outside is whatever it needs to be. Okay, so I was going to be kind of careful about that. Okay. Now off to the side again. Okay. So walking into this class, there's not a lot of formulas that I necessarily expect people to know from a trig class, but there is one that I expect every single person to know. Sine squared plus cosine squared of x. What is that? Equal to? That's equal to 1. Yeah, good. That's equal to 1. Yeah. Okay. Now, there's a couple other formulas you're going to need to know down the road. We'll get those. We'll get those out of the way when they come there. But this one I expect everyone to know at this point, and you're going to need to know it as well, folks. This is one's going to come up on a pretty regular basis through some of the sections. So make sure you know it if you don't have it down. Okay. Now, I'm not going to use this formula per se here, but what I am going to do is acknowledge, yeah, if I wanted to, I could take this formula here and I could simply subtract cosine squared from both sides and have then sine squared is 1 minus cosine squared. Yeah. Simple enough. Okay. Well, I'm going to do that. So equals there. So equals here again. So still got my lone sine sitting here in front of my integral. Okay. Bracket there. Again, I'm going to take my sine squared and rewrite it in terms of cosine using this formula over here. So 1 minus cosine squared of x squared dx. Okay, now, everybody follow with that. Again, we're not worried about the y's, yeah? Just following the individual steps. In fact, let's go back and rehash our individual steps. What did I do? So I took my sine to the 5th, and because I felt like it, I stripped one sine out, left the other 4 here. So sine times sine to the 4th, yeah, basic algebra. And then because I felt like it, and again, we're not going to worry about y, yep. As long as this is an even number, and that's super important, folks, it has to be even. We'll kind of come back and touch on that here in a minute. As long as this is an even number, this is easy to do. Squared to something, yep. Now I can do it if it's an odd number. If this had been, say, a 5, squared to the 5 halves, I can do that. Trust me, that just put me into the next section, and you guys are going to have nightmares about the next section. Okay? So you don't ever want to do the next section unless you're forced to. So I don't want an odd number sitting here. I want an even number sitting there. Okay, so I can keep this as an integer sitting right there. Okay, so squared to an integer, meaning even number here. Okay. And then because I felt like it, I said, you know, I can take this sine squared, and I'm going to write it in terms of cosines because I feel like it. Right? Again, we're not worrying about the y's still, just individual steps. Algebra, trig. That's all that is. Yeah, basic stuff, quote unquote. Okay. Now, why did I do all of this stuff? Well, remember what I said when I started this problem. I said what? I said this is a basic calculus 1 substitution, right? It just isn't sine. So what is it? How about cosine? Yeah, because what do I see here? I see a cosine squared here, so what's that going to become? That's just going to become a u squared, right? Once I do my substitution, right? Oh, and by the way, folks, I'm usually not going to write the differentials down for these. At some point, I'm going to leave it up to you guys to say, hey, y'all can do the work. I'll do the first couple of them, right? What's differential? Differential is minus sine of x dx, yeah? Oh, and what do I see right there? It's missing the minus sign, but who cares? We can deal with that. Yep. Okay. I can always take that minus sign and move it over there if I want to. Right? So sine of x times dx. So again, what do we have there? This stuff here then is just simply minus du. That's all that is. Yeah. Okay. There's my cosine squared there. That's just u squared. So upon doing my substitution, what do we have here? Well, I've got that minus sign on the du. I'm just going to go ahead and factor that out of my integral just to kind of get out of the integral. Sine of x dx, well, that's just the du again from minus sign there. Yeah. Then I've got, don't forget your brackets and your product or your exponent here. Yep. So bracket 1 minus cosine squared. But cosine is u, so 1 minus u squared. Quantity squared. Yeah. Okay. Everybody kind of follow that step. Yep. Okay. Now we'll come back and finish it out in a minute, folks. But this to this point, this is just straight up Calc 1. Yep. Okay. So we'll talk about that in a minute. A little bit different than what we saw in Calc 1. That's straight up Calc 1. Now, again, back to the original part step of this problem, folks. This worked. Why? Why did this substitution work for me? Well, it worked for me because I had this sign sitting here. Yep. Okay. Without this sign sitting here again, this cosine substitution would not work because I couldn't have this sign down here in the differential that needs to get sucked up. And it's not there, but now it's there. Right? So again, without that sign, again, this won't work. So I had it. Well, how did I get that sign in the first place? Actually, I'm going to step back. Where did the cosine come in the first place? Well, the cosine came because I used a little bit of trig here. Yep. I was able to do that because I had a squared to an even power up here, which again required an even power sitting right there. Yeah, I shouldn't say even power here, but squared to a number because we had an even power here. Yep. Now, where did the sign came from? Well, the sign came from because I took my original thing and I stripped out some. Yep. Okay, so how did I know to do this? Well, again, looking back for what I want here again, I want to be able to do this substitution here and have something easy to deal with here, i.e. something that's not a fraction, because that puts me in the next section. Right? So I want an integer here, which if I want an integer here, that means I had to have an even number here, and I needed this sign sitting out in front here. Right? Well, the only way I could do that is if what? Is if that thing there was an odd number, right? So if I've got an odd exponent sitting here on this sign, what can I do? I can simply take one of them, strip them out. What's going to be left over then is an even number. Yep. I can convert the even number to squared to whatever I need it to be. Okay. And then the sign squared here, I can convert over to cosines using our formula here. Right. So if this had been, say, a 15, wouldn't want to do this. If it had been a 15, what could I do? Strip one of them out. I hope. Okay. Yeah. Okay. And Casey, I'm assuming that means I just covered the stuff for your question, I hope.
So you, yes, we got it. However, you dropped out for maybe about 20 seconds for the online class.
Oh, I'm sorry.
Okay.
I didn't realize that we had dropped out. I apologize for that. There was no indication here that the dropout had happened. I'm sorry. So, where do I drop out?
You were discussing how we got to this 1 minus u squared parentheses squared.
Okay, so let me just kind of go back and kind of rehash everything then. So just to make sure. I kind of just probably what I guess got them doing when I lost you guys. But so again, what we're doing here, we've got this bit down here again. This substitution worked, okay, because well, like I said, it worked, but I wanted to do this substitution here, and I used it because I had the cosine squared here. Where did that come from? That came from the sine squared sitting here, right? And where did the sine squared here come from? Well, that came from the fact that because I had an even number here, I could write it as squared to something. Okay, now again, something could be whatever it needs to be. Again, I'll come back and hit this in a minute again. But because an even number here, I could do that. Okay? And it also worked because I had the sign that I need for my differential sitting out in front of my integral right here. Okay? Where did that come from? Well, that came from here, that came from here, and ultimately it came from the fact that I took my original problem and I stripped one of them out. Okay? Now, again, going through a little bit quicker this time. Because I had an odd number here, this works. So again, let me take a different number this time. I used 15 last time. Let me go with, I'm going to go with 21 this time. Yep. Again, way too big to do for this problem, but 21. 21's obviously odd. So I can take one of my signs, strip it out here. Okay? I'll have 20 of them left over. And because 20 is even, I can always write it then as 2 to something. So in this case, 2 to the 10. Yeah. Okay? And because I've got a squared here, I can sign squared here, I can use our formula from over here to write that as 1 minus cosine squared. Just basic trig formulas. Yeah. Okay? At that point, I can say to myself, oh, geez, I've got cosines, a bunch of cosines here, and there are a bunch of cosines here, right? You agree with that? Because eventually I'm going to have to actually square this out, or in our case, my number here, raise that to 20. So it's a bunch of cosines here, right? We got a bunch of cosines sitting here. And so I went thinking, okay, well, I could try u equals cosine. That would tell me my differential is sine times dx. Oh, and again, I've got exactly what I need down here for my differential to work. Yeah. Okay, so this stripping this one sign out gave me the sign that I needed for this substitution to work, which case we can do substitution. Okay. All right. So hopefully that gets everybody caught up. So questions up to that point. Yes, yes, we have, yeah, this has to be a square, okay? So we can use this basically to convert to the other one, right? Now, and of course, not only that again, not only that to be a square here again, this needs to be an even number. Like I said, if it's odd, if this is an odd, I shouldn't say not, sorry, not even number here. This has to be an even number here. Oh, sorry, there it is, right? Again, if this is an odd number, say a 5 again, yeah, I can write this 5 halves. Right? But again, the minute you put a fraction out here, you're in the next section. And again, like I said, you guys are going to have nightmares about that next section. Not want to do it. It's going to take about 3 days to lecture on that section. Okay, so you can see if it takes me 3 days, it's not a fun section. Yeah. Okay, so you want an even number here. So a squared there and an integer out here. Okay. All right. Now, as the rest of this here, then, folks, this technically then is a quote unquote simple Calc 1 integral. Okay. Because all you have to do then is, of course, square this out. Yeah. So I'll kind of run through the work real quickly here. So square it out, yep, because we have to square that out to do the integral, yep. Okay, so we have to square that out. At this point, again, just got a bunch of u's here. I did say there are a bunch of u's here, right? Which is also why I said, right, you don't want this thing too much bigger than a 2, yep. Because even if I'd had a 7 up here in my original problem, that'd put a 6 here, that'd put a 3 there, a 3 there. Oh, it would put a 3 there, which in theory we're all capable of doing, but I don't want to cube that out. Yep. Okay. So generally speaking, I try to keep these down as small as I can. Okay. You might see the occasional cube, folks. That'll be homework exams. Okay. I won't put anything past a cube, though. I'll guarantee that. Okay. All right. Or I should say that I should be careful. I say that there are ways to do it without going past a cube. Let's say that. Okay. We'll see how that works here in a little bit. Oops, u to the 4th. Yep. Thank you. Sorry about that. U to the 4th. Sorry about that. Be careful when you're doing this stuff. Try to not get too much of a hurry. Sorry about that. Okay, now integral. Rest of this stuff here. So let me work backwards here at some level. Yeah. So see why I'm working backwards here in a second. So integral of u to the 4th. That's 1/5 u to the 5th. Yep. Again, I'm not going to write that down. I'm going to go ahead straight back to the fact I know what u is. It's cosine. So I'll slide over here. So 1/5 u or cosine to the 5th. Yep. Plus there. Okay. U squared, 2u squared. Well, again, u squared is just a 1/3 u cubed. So with the 2, so 2/3 u cubed. So u cubed, or again, cosine cubed because u being cosine. Yeah. Okay. What's the integral of 1? Somebody help me out, please. Not x. Yeah. Everybody always wants to say x. And I get that because we do a ton of x's in Calc 1. Yeah. Okay. Integral of dx, or be careful here. Yeah. 1 obviously doing something different here. integral of 1 1 dx. I'll give you any day of the week that's x. Right? But I'm not doing integral of 1 dx. What am I doing? I'm doing integral of 1 du. Right? So let's try again. It's not x. It's what? It's u. Yeah. Remember that. Yeah. When you integrate a number, folks, a number 1 by itself is what usually where folks get in trouble with this. When you integrate a number by itself, remember, folks, it always goes back to that du or that differential there. Yep. So this would have been an x had it been doing dx. But I'm not doing dx, I'm doing du, so it's got to be a u. Yeah. So let's kind of do 2 steps here. So this integrates into a u, which in turn integrates back into a cosine. Yeah. Okay. Had that been a t or something like that, it'd be a t. Right? So just be careful when you do that. It's one of the biggest mistakes people make with this when they start doing this problem. Okay? Yeah, I always got to be really, really, really careful with that. Okay, one thing I'm missing next, I kind of work backwards here. I'm missing my minus sign. Yeah, and I guess I'll tack the plus c on as well. Each time. Okay, everybody follow with this. Yeah. Put parentheses on. Yeah, good. Thank you. Yeah. So again, made an obvious mistake here again, folks. You've got a minus sign in front of my integral here. So that means I need a minus sign in front of my integral. Yeah. So brackets. Okay. So either put the brackets in or distribute it through if you wish to. It's up to you and how you wish to do that. I don't particularly care. WebAssign is definitely not going to care either. Okay, which way you do. Okay. All right. So tricky problem at some level. Yeah. Everybody kind of follow what I did with that. Yeah. Okay. So, I'll point out here, folks, I'm not going to do this because we don't have the time, of course. I could have, if this had been a cosine to the 5th, I'd do pretty much the same thing. Yep. If it's a cosine to the 5th, what would I do? I'd strip 1 cosine out. I'd have cosine to the 4th left over. Yep. Okay. And then I'd say, okay, cosine to the 4th is cosine squared. Oh, so what's cosine squared? Cosine squared is 1 minus sine squared. Yep. Okay. And I'd say, oh, okay, I've got my cosine sitting out here, 1 minus sine squared here. We'll do a u equal to sine because du is cosine dx, which is exactly what I would have here. Yep. Okay. So I'm not going to write that out, but the process I use for sine is identical for cosine in this case, right? Okay. Now, don't have time here. Don't have a ton of time left here, folks. Let's see if we can at least think about another problem. Okay. So I'm going to apparently change things up pretty significantly on it, but it's not as different as it looks like. Okay. The first one had just a sine or just a cosine. We talked about just a cosine. Okay. Doesn't have to be that though. Brett and tangent, yeah, tangent's totally different, and that's tomorrow, probably. Okay. So we'll take a look at tangent tomorrow. Definitely different on that one. So but good question, which we'll do it tomorrow. So actually we'll do secants tomorrow as well, actually. So okay. Now, what happens is you've got sines and cosines, and kind of to your question, Britton, as well, they do have to be sines and cosines at this stage. Yeah, I don't want to be mixing and matching. Okay, so no, not sines and tangents or something like that. Sometimes those can be done, but we'll talk a little more about that down the road, I'm sure. But sines and cosines only. Oh, and products here, folks. Right, one product sitting there. And I want the same arguments that both x's or both 3x's or both 5x's or both 10x's or something like that. Cosine is there. Yeah. Sorry about that. Yeah. It's always a little bit small sometimes. So yeah. So sine to the 6 times cosine cubed. Now, general process, folks. I did the first problem with just a single trig function, so I wanted to get the process down. Okay. But the process will work even if you have a product of things here. Right? So what you have here is you want to say to yourself, okay, I see a product of sines and cosines. I'm going to eventually either do a u equals sine or a u equals cosine substitution. Okay? What that means is I need one trig function floating around by itself. Okay, all the rest of them have to be converted to my other one. So I want a single sine and a bunch of cosines, or I want a single cosine and a bunch of sines. Okay, that's what I need to have for this problem to work out. And the process I used up above is the same process here. Okay, so I need to strip one out, convert the rest to the other one. Same process. Okay, now I'm not going to write this down. Let's just think through in our head here a little bit. If I strip one sine out, which I can do, yeah, I can always write this sine to the 6th as sine times sine to the 5th, right? Now, what's the problem with that sine to the 5th? It's an odd exponent, and I don't want that odd exponent. Because again, I could write that as squared to a power. That power would be 5/2. It's a fraction. Next section, we run away screaming, right? So we don't want to do that, right? So stripping one sign out is not a good idea here because it leaves me with an odd number that I have to convert to cosines. I do not want to do that, right? Lucky enough for us, what do I see on the exponent for cosines? It's an odd number. So if I strip one out of there, what do I have left over? I got even number left over. Yep, that's what I want to do. Now, I'm sure the question is out there, folks. What if they're both even? That's tomorrow as well, right? Both even is a totally different situation, right? So don't worry about both even. Both odd, we'll talk about that when we get to the end of this problem, okay? But in this case, I've got an odd number here on the cosine. So let me go ahead and at least get started on this. We may not get it all the way done. So cosine cube here, dx, all right? And let me just kind of move it down here so I got more room to right here. So again, I'm going to strip one cosine out. I usually put these either out in front or out behind here. In this case, I'm going to put it out in front. Just to kind of make it clear, this is the bit that I'm stripping out. Okay, got my sine to the 6 here. I'll leave a little bit of space there to kind of keep in mind what I got going on here. That's the one I've stripped out. I've got my sine to the 6, and then I've got 2 cosines left over. Yeah. Okay, so again, my cosine cube became the cosine there and the cosine squared there. Yep. All right, I'm just kind of just keep coming down the line here. Okay, now, again, sine to the 6th. Leave this alone, folks. Okay, I stripped one cosine out, so that means I need to get rid of, or should I get rid of? I need to convert my remaining cosines into sines. Okay, so I don't worry about these signs here. Okay, so I've got the cosine I stripped out. I've got the sine to the 6 left over. Don't care about that. This is just straight up squared, so I don't have to worry about converting exponents. Yep. Had this been, again, say an 8, it'd be squared to the 4. Okay, that'd be my next step, but in this case, I kind of kept it simple for us. Just a straight up cosine squared here. I know what that is. That is 1 minus sine squared. Yep. Okay, so again, make sure you use different color here. Cosine squared, 1 minus sine squared there. Yep. Okay. Probably use different color there to make it clear what I was doing. There we go. And then dx. Okay. Now, this is also why I don't worry about the signs. You don't convert these because now what do I see? I see a bunch of sines and a lone cosine out here by itself. So what can I do? I can do u sine. Yeah, I can do u equals sine of x. Yeah, because again, what's du? Du again is just straight up cosine of x dx, which again, cosine of x dx, right there. Yep. So again, kind of strip these out here. That is just straight up du. That's all it is. And then all the rest of this stuff here are our u's. Yeah. Okay. So down here, integral u. Oh, sorry, not u. Sorry, du. So strip it out here behind. Sorry. So my cosine is going to become my du. Yeah. I see a sine to the 6 here. Well, that means that's just u to the 6. And then bracket 1 minus u squared. Does that make sense to everybody? Yeah. Again, I think it's probably a little bit easier to see once you see what you got to do. Yeah. Okay. Not easy to see you had to do it once you see what to do, not that. Hopefully. Yeah. Okay. We're almost done. Almost out of time, so we're almost done as well. Of course, to integrate this, we got to distribute it through. So u to the 6 minus u to the 8 du, and then 1/7 u to the 7th, or again, oops, sine to the 7th, minus 1/9 u to the 9th, or again, sine. Again, we're done with our integrals here, done all that, so plus c. And there we go for an answer. Oh, and folks, by the way, I was doing a little bit of highlighting yesterday. Just to kind of warn you real quick on this. I learned when I exported a file from my Calc1 class, highlighting kind of obscures the writing, so I can't really highlight stuff anymore. It sucks. So I want to be able to highlight things a little bit, but it doesn't export well. Okay, so I'll try to do things more like this rather than highlighting the actual answer itself, which is why I'm kind of putting them below. So, okay, does this make sense, everybody? Yep. Okay, now real quickly here, folks. I know we're kind of out of time here, but real quickly. Sine to the 7th I'm not going to actually work this one. Just acknowledge what happens. You know, what happens if they're both odd? So a cube and a 7. What could I do? Well, I could do the same thing I just got done doing. I could strip one cosine out, convert the other cosine to sines, yeah? Or I could do what? I could strip one sine out, sine to the 6, so sine squared cubed, convert those to cosines, okay? So if I got both odd, I can strip one out of one or the other. Which one should I strip out in this case? Cosine, because if I do the sine, that's sine squared cubed. Eventually, I'm going to have to deal with a 1 minus u squared cubed. I'm going to have to cube out, yep, right? So if they're both odd, in theory, you can do either one. Strip one cosine out, strip one sine out, doesn't matter. But in practice, which one should you always strip out? The lower exponent, because that's less work for you guys in the long run, right? So make sure you do that. You work, and everything should work out for you, okay? All right, perfect spacing here. So we'll do what happens if they're both even tomorrow. Those are a little bit trickier to deal with, so we'll do those tomorrow. We'll also at least start talking about secants and tangents tomorrow as well, okay? And what's tomorrow? Tomorrow's Friday, yeah. Friday. Then that's going to mean I'll finish this section out, or at least enough for the homework on Monday. So I suspect the homework's going to stay Wednesday, folks. Okay. We'll have a help session on Tuesday. I'll formalize that up probably Friday or Monday for sure, but I suspect homework's going to stay Wednesday. Okay. So let's kind of let you know about that. But good place to stop here for the day. So we'll stop here for the day, and I will see you all tomorrow. I'll stick around a minute or two for questions if you got them. But if not, you are free to leave at this stage.